Hello friends, today we will talk about the use of Sommerfeld number in general bearing design. When we are talking about the Sommerfeld number is nothing but is a dimensionless number. And this dimensionless number contains the terms which are very well associated with the journal bearing. If you see the Sommerfeld number, it is represented by capital S, and the mathematical formula of the Sommerfeld number is S is equal to R by C square multiplied by Zn by P multiplied by 10 to the power minus 6. So if we see this formula, this first term R by C is nothing but it is the inverse of radial clearance of a journal bearing, because C is the radial clearance and R is the radius of the journal. And we see the second term of this Sommerfeld number is nothing but it is the bearing characteristic number of the bearing, journal bearing. So this N is nothing but a rotation per second, although we take the bearing characteristic number as Zn by P, that is where we take capital N, that is the RPM of the journal. Here we are taking the small n, make it dimensionless, the unit of the journal, this Sommerfeld number dimensionless. So we have taken it as a per second. And the second is the R is the radius of journal, C is the radial clearance, Z is the dynamic viscosity of the lubricating oil, and P is the pressure. So this Sommerfeld number is very helpful to design for the designer when they are designing the your journal bearing, because it includes the design parameter. And what are the design parameters? First thing is the dimension of the bearing. So if we talk about the dimension of the bearing, it contains the diameter of the journal and diameter of the bearing, and this two things can be included in this Sommerfeld number as a radius of the journal and the clearance. And if we know the radial clearance, then we are able to find out the inner diameter of the journal. Okay, then second thing is the property of the fluid, that is the viscosity of the lubricating oil. So we have included in the Sommerfeld number as Z. So that is the dynamic viscosity. Then the speed of the rotation of the journal. If you see this whole number, it contains all the parameters which are very important for the journal bearing design, because clearance is very much required to develop the oil film in between the bearing and the journal. Viscosity of the oil is very much required to have the ability to sustain the load, radial load, for which the journal bearing is designed. This N is the cause of that film which will be developed between the journal and the bearing. So this is one of the more important parameters, that is the rotational speed of the journal. And P is the pressure, that is that include the term of the radial load and the dimension of the or the length of the bearing. Okay, so this Sommerfeld number is given by inverse square of the inverse of radial clearance ratio multiplied by bearing characteristic number. You can remember this formula like this. Sommerfeld number is nothing but it is the square of the inverse of radial clearance ratio and the bearing characteristic number, and at the end you have to make it as a dimensionless number, so you have to multiply by 10 to the power 6. Okay, now how to use this Sommerfeld number for the design purpose? So many design variable and the characteristic can be found with the help of Sommerfeld number, as there are hydrodynamic bearing characteristics are plotted against the different Sommerfeld number. One thing more is remaining in this Sommerfeld number. One more important functional relationship is not included, or you can say the one most important parameter is not included in in the Sommerfeld number, which is required for the design, that is the bearing arc angle. Because we know that the journey bearing are not always the 360-degree bearing. Sometimes it may be partial bearing, sometimes it may be tilted pad bearing, or sometimes it is multi-pad bearing. So this bearing arc value is very important when we are designing the journey bearing. So to include this bearing arc parameter in our design, what we do, we draw the several characteristic curve for the characteristic of our interest for different arc value. And whenever whatever is the requirement, what type of bearing we are designing, we consider that curve for the particular design. Okay, so many design variable and the characteristic can be found with the help of Sommerfeld number, as there are hydrodynamic bearing characteristics are plotted against the different Sommerfeld number. And characteristics are different plotted against the Sommerfeld number, and for the at the same time they are plotted for the different arc value. Okay, so the most three important characteristic curve which are plotted with the help of Sommerfeld number are the coefficient of friction variable, where the coefficient of friction variable is given at coefficient of friction multiplied by R by C. We multiplied this R by C with the friction, coefficient of friction to include the design consideration for the particular application, because the curve is drawn for the journal. Okay, if we are not including the R by C or the design parameter, so we cannot find out the particular value of the particular application. So this by multiplying R by C, the friction value is related to the particular application. Okay, as well, and when we are multiplying on the same time, this friction is remain the dimensionless, because R and C are in M, so it is dimensionless. The friction coefficient is also dimensionless. Other important curve is the Sommerfeld number versus flow variable. Although this curve is the volume flow rate versus Sommerfeld number, but we made this volume flow rate dimensionless. Why we are making it dimensionless? To connect with the particular design. So we divide this flow rate with the specific application parameters, that is RC into NL, where R is the radius of the journal, C is the clearance, N is the number of RPM of the journal, and L is the length of the bearing. And another important curve is the dimensionless minimum film thickness versus Sommerfeld number. Or this dimensionless film thickness is made dimensionless by dividing it by the radial clearance value. So these three important curves, and these important curves are given in your machine design data book written by Reddy and Mahadevan. So in your book, you can see these curves, how they are plotted. So I'll just show you the curves. The first curve is friction variable curve versus Sommerfeld number curve, and this is here you can see. If you see this curve, it is just like the journal bearing characteristic curve drawn for the 360-degree bearing, and because this is nothing but it is a your bearing characteristic number. Okay, so and it is multiplied by the R by C. So this curve and then values of the curve are slightly different, but the nature of the curve is same. Here in your data book, this small n is converted by capital N. That's why they are writing at second per minute. So this on the x-axis, the Sommerfeld number is plotted in second per minute. Okay, so need not to multiply or divide by anything. Here another curve is the flow variable curve. you can see here the Sommerfeld number in second per minute versus Q by RCNL. So you can have this curve from here. So in that case, you will have the value in value of flow rate in per minute. Okay. Now, next is the your H naught by C curve. This H naught by C curve is nothing but is the dimensionless minimum film thickness versus Sommerfeld number. So again, you can find out if you know the Sommerfeld number, you can find out the H naught by C, or if you have the minimum film dimensionless minimum film thickness, you can find out the Sommerfeld number, and you can find out the required variable or the design variable which you want to design. Okay, so now the question arises how to use these curves in a design problem. So we'll take a design problem, and I have taken a design problem which was asked in your university examination 1819. The problem is following data is given for full hydrodynamic bearing. Radial load is equal to 25 kilonewton. Journal speed is equal to 1000 rpm. Unit bearing pressure is 2.5 megapascal. Viscosity of lubricant is 20 centipoise. L by D ratio is 1. Ratio of minimum film thickness to radial clearance is equal to 0.25. And we have to determine the dimension of bearing, minimum film requirement, and requirement of oil film. The interesting thing here, the minimum film thickness to radial clearance, that means the dimensionless minimum film thickness is given as 0.25. Okay, so we'll to proceed this design problem, first we will write down the given data. That is, given data is radial load is given on 25 kilonewton, that is 25,000 newton. Shaft RPM are given as 1000 RPM. Pressure is given as 2.5 megapascal. Viscosity of lubricant, that is dynamic viscosity of the the absolute velocity, is given as Z is equal to 20 centipoise. That we have to convert in Newton second per meter square. L by D ratio is given is equal to 1, and dimensionless film thickness H naught by C is equal to 0.25. For dimensions of the bearing, we have to use the pressure. As we know, the pressure is equal to load upon projected area of the journal, and the projected area of the journal is equal to L into D. So pressure is equal to radial load divided by projected area, L into D, and we have the L by D ratio is equal to 1, so we can find out the D value, and the value of D comes, that is the diameter of the journal, comes out 100 mm, and the length will obviously be as L by D ratio is given as 1, so L will be equal to, length of the bearing will be equal to 100 mm. Second part we have to do is find out the minimum film requirement. Minimum film requirement, if you see, the minimum film thickness is dependent upon the your surface roughness of the journal and the surface roughness of the bearing and the machining factor. If you see the mathematically, the machine film thickness, the minimum film thickness is calculated as minimum film thickness is equal to machining factor multiplied by root mean square value of roughness of journal plus root mean square value of bearing. But if you see in this problem, neither the roughness of the bearing in the journal nor the machining factor are given. When we are talking the machining factor means what type of machining we are done on the journal. That journal is polished, journal is rough machine, journal is well grounded, whatsoever. Okay, so but nothing is given in this problem. So to solve this problem, we will use the Sommerfeld number versus dimensionless minimum film thickness characteristic curve, that is given in your page number 356, figure number 15.9 in your machine design data book written by Mahadevan and Reddy. So this is the curve. So what we will do, what is given to us, we are having the H naught by C, that is the dimensionless minimum film thickness is given, that is 0.25. And we are having a curve H naught by C, that's a minimum dimensionless minimum film thickness versus Sommerfeld number. So we will try to find out the Sommerfeld number from here. So we are having H naught by C, and H naught by C is on the y-axis, so we will mark 0.25 on y-axis and transfer this point on the 360 degree beta is equal to 360, because it is given in your problem that full hydrodynamic bearing. The full hydrodynamic bearing means 360 degree bearing. So we will mark this point and like this. We have marked the 0.25 point on the y-axis and transferred it on the beta is equal to 360 curve, and then this point is again transferred to the x-axis like this. So from here we can read out the value of S, that is R is by C whole square Zn by P multiplied by 10 to the power minus 6. This is written here. Okay, so this value comes out 1.25. So we have equated this value 1.25 is equal to R by C square multiplied by Zn by P into 10 to the power minus 6. This value comes out from this graph. Now, what is not known in this formula? We see the radius of the journal is given in your previous step. We have calculated this value. Diameter of the journal is given calculated in the previous step. So radius of the journal will be equal to 50 mm. Clearance we don't have because we have H naught by C, but we don't have the clearance value. We see the viscosity, dynamic viscosity, which should be in Newton second per meter square, but we are having the viscosity in centipoise, so we will convert it into the this value into the Newton second per meter square by multiplying the value of 20 into 10 to the minus 3. We will convert it into Newton second per meter square. Okay. Rotational value, RPM are given in the problem, pressure is given in the problem. So again, the only unknown thing is the C. So we can calculate the value of C as root of this R square by S multiplied by Zn by P into 10 to the power minus 6. So we have calculated the value is equal to of the radial clearance is equal to 0.126 mm, and we are having the ratio of H naught by C as equal to 0.25. So we can easily find out the minimum oil film thickness from this. That is H naught is equal to 0.03. Okay. Now we have to calculate the oil flow rate required for the bearing. So to calculate the oil flow rate required, what will we do? We will use the flow variable versus Sommerfeld number graph. So this graph is the flow variable versus Sommerfeld number graph. Okay, we have calculated the Sommerfeld number in the previous step, and that Sommerfeld number comes out 1.25. So what we will do, we will mark 1.25 on the x-axis and transfer this point on the graph. Beta is equal to 360. Then we will transfer this intersection point of vertical line and the graph on the y-axis, so that we are able to have the value of flow variable. And when we have transferred this point on the y-axis, we have got the flow variable is equal to 1.25. Now we are able to equate this flow variable is equal to 1.25. When we equate this value, flow variable is equal to 1.25, then the flow rate can be calculated. Okay, the flow rate can be calculated. We know the radius of the journal, that is 50 mm. We know the radial clearance, that we have calculated in the previous step. That is C comes out 0.126. So we are able to find out the radial clearance C. we have we are having the number of RPM of journal, that is 1000. We have calculated L is equal to 100 mm in the first step, and we are having the flow variable is equal to 125. So we are able to find flow rate. The flow rate from this calculation will come out in the mm cube per minute. This is the volume flow rate in mm cube per minute. To convert it into the meter cube per minute, what we have to do? We have to multiply with this multiply this value with the 10 to the minus 9. So we are able to find out the flow rate in meter cube per minute. Suppose in some question it may be asked that find out the flow rate in kg per minute or kg per second. In that case, you have to do nothing but you have to multiply this flow rate with the density of the lubricating oil. In that case, you will have the flow rate in the kg per minute. Okay, so in this manner you can attempt the design problem with the help of Sommerfeld. Thank you for watching me. Thanks again.